Yeah.
Hello, my name is Briseida.
I'm Benjamin.
I'm Robert Grathwohl.
So you want to do the test?
It's all lined up.
Yep. Good deal. Alright, my name is Travis, and I'm going to show at what point on the beam does the linear acceleration equal that of gravity. So we have this beam, and we know that the total distance is some distance L. And we went to the center of axis is right here, because it's mounted on the table. And we want to find the linear acceleration at some arbitrary distance d that lies along the linear side of the beam. So we'll call this, rather than calling it d, let's call it r. Okay. So we know that so we want to find the moment of inertia anchored at that point. We know that the moment of inertia in the center of mass is equal to 1 over 12 times the mass times the length squared. But we want to find it for that point, so we can use the moment of inertia at the edge is equal to mass times distance squared plus 1 over 12 mass times the length squared. This is the, what's it called?
Moment of inertia.
No, what is this equation called? It's the
Parallel axis.
parallel axis here, thank you. And so we know that through the center would be right here, that's L over 2. And so we can just plug in L over 2 for our d, so we get I, the edge, is equal to m times L over 2 squared plus 1/12 m times the length squared, and that would come out to 1 over 3 m L squared. All right. So that's our moment of inertia at the edge. So now we want to find, for some arbitrary distance r, the linear acceleration. So we can use our torque equations. We know that torque is equal to the moment of inertia times angular acceleration. We also know that torque is equal to r cross F. However, our r distance and our force are perpendicular, so we can just change this to r times F. Okay. So what we do is we set these equal to each other. So we have moment of inertia times angular acceleration is equal to r times F. And now we simply plug in some variables. So we know that F at that point would be F is equal to ma. Our acceleration is due to gravity, so we have F is equal to mg. And we can also use our moment of inertia that we found there. So we have 1 over 3 times the mass times the length squared times angular acceleration is equal to r times m times g. So right here, what we can do, we can cancel out the m's, and we want to solve for r. But first what we want to do is we want to replace this with our linear acceleration. So we use this equation. Our linear acceleration is equal to distance times angular acceleration. And we simply rearrange that to get that the angular acceleration is equal to our linear acceleration over our distance. And so we simply plug that in right there. So now we have 1 over 3 times the length squared. We plug that in. Linear acceleration over our distance is equal to our distance times gravity. What we also know is that we want to find the point at which our linear acceleration is equal to gravity. So instead of just using linear acceleration, we can plug in g for that value. So what we get is we get 1 over 3 times the length squared times gravity over our distance is equal to our distance times our gravity. So now these gravity values cancel out. We multiply both sides by r. So we get L squared over 3 is equal to r squared. Take the square root, I'll do that over here. We get r is equal to the square root of our length squared over 3. Now we measured the length of our rod, and we found out that the length is equal to 2 feet. So whenever we plug that in there, we get r is equal to the square root of 4 over 3. This is in feet. And that comes out to approximately 1.15 feet. So at about 1.15 feet from the edge, there's a point here that travels that has a linear acceleration the same as gravity.
All right, good job.